Okay, this is the most difficult of the examples that we're going to have here on substitution because of the way the substitution works on this one. When you have the degree of the inside one more than the degree of the outside, then your substitution is straightforward. In this situation, though, we have the degree of the outside equal to the degree of the inside, and so it could be done by U substitution, but it's not easy. But, let U be what you would think it to be. The thing that's underneath the root, let U equal x minus 1. We have to substitute for x minus 1, which is just going to be a U. It's going to be the root of U in the denominator. But we also have to substitute for x and for dx. Substituting for dx won't be a problem. We'll just take the derivative. Du is dx, so no trouble there. Here's the issue. Substituting for x. Right now, there's nothing to say what x is. If that had been an x squared minus 1, then everything would have worked out nicely, because if that was x squared minus 1, then when we take the derivative, the x would show up in the derivative. And so, had this problem instead been x over x squared minus 1, then our life would have been made easier, because when we go to take the derivative of x squared minus exactly 2x dx, and that x would show up, but now there's no x showing up. It's a mystery. What do we do with the x? The answer to that mystery is to solve for it. Strangely enough, it'll work for us if we take the u equals x minus 1 and solve for x. Add 1 to both sides and get x is equal to u plus 1. So that's what's going to take the place of x. Also, at the same time, let's do a limit switch. Usually with this kind of a setup, limit switches work great. If u is equal to x minus 1, your original substitution, let's go figure out what your new upper limit is. Currently it's a 5. And we need a new lower limit. Currently it's a 2. We need to change these x's into u's. Plug into the substitution. 5 minus 1 is 4. 2 minus 1 is 1. So your new upper limit is 4. Your new lower limit is 1. So here's your new integral. You're going from 1 to 4. Your numerator is u plus 1. That's what x is. Your denominator is the root of u from your substitution. Dx is du. So how did that get better? Why is this more desirable than what we had before? With a single term in the denominator like this, we can take the two terms that are in the numerator and divide them each individually by this single term. So we could take u over root u and 1 over root u. And that's great, because then we have something that looks like two individual terms, which we can quickly use the power rule in reverse on. I mean, they're not polynomial terms, but we can do the power rule in reverse. So u divided by root u is just a root u. If I have u to the 1 and u to the half, and I divide, I subtract the exponents, and I get u to the half. One way to look at it. And then this guy, I'm going to call that u to the negative a half. So I'm ready to use the power rule in reverse on that. So I have u to the half and u to the negative half from 1 to 4. And I don't have to go look back and see what were the original x's. I can now just look forward. The answer to the original question, the area under that curve from 2 to 5, is the same as the area under this curve from 1 to 4. We traded it in for a much simpler integral. This was brought about by the fact that our substitution had the same power as the remainder of the integrand. And so the normal substitution works, but then you have to solve for the x that's in the rest of the integral, and then plug in for that. So now we're ready just to finish this off. We add 1 to the power rule in reverse, add 1 to the exponent, divide by the same thing. We have a half. Add 1 to it, we get 3 halves. But instead of dividing by 3 halves, we'll multiply by 2/3. And then we have a negative a half. Instead of dividing by a half, we'll multiply by 2. And let's go back into root. It'll make it easier to evaluate if it's a root. So u to the 3 halves over 3 halves, u to the 1 half over 1 half will become 2/3 of u to the 3 halves plus 2 root u. And this is just announcing that you're about to plug the 4 and the 1 in. You don't have to look back and wonder, oh, should I really have done 2 and 5, the x numbers? No. When you do a limit switch, there's no looking back. If it's done correctly, you just move forward from that point on and you get the same answer. So next it's our job to plug a 4 in, and then plug a 1 in and subtract to use the fundamental theorem of calculus. Okay, so we have 4 to the 3 halves, and then a root of 4, 1 to the 3 halves, and then a root of 1. Okay, 4 to the 3 halves is an 8. That's the only mystery of these here to calculate. And you know that comes from the fact that 4 is actually 2 squared. So that works out great. It's an 8. So here we go. Let's finish it out now. We have 2/3 of 8. We have 2 times a 2. The root of 4 is 2. And these 1s to powers are just 1s. So we take 2/3 plus 2. And then the subtraction is from the fundamental theorem, upper limit evaluation minus lower limit evaluation. So we have our 16/3 plus a 4 minus our 2/3 minus a 2. Distributing the minus across and making this guy 16 over 3. Let's go ahead and put these two together and call it 14 over 3. Put these two together and call it 2, and now we're almost done. Rename 2 to be 6/3 together with the 14/3, and you get your 20/3 as your answer. 6/3 and the 14/3 make your 20/3. And so that's the answer to the question, 20/3. And it's brought about by the power of the inside function matching the power of the outside function. So this substitution works, but you have to sub by solving for the x. It's kind of strange, but that's how it works.